Раз, раз. Добрый день. Я потерял докладчика по дороге, но он сейчас придет. Самое интересное, что вот он шел, дошли до лифта, и я сюда вошел, а он куда-то исчез. Ну, может быть, в туалет заходил. Единственное, что мне в голову приходит. Okay, here is our speaker. He arrived this morning to Russia from Spain. He's now
Like this?
the professor in our university.
Is the first one.
Just today, I got to know that he's the author of more than 700 publications. 700. It's, to my mind, it's incredible. Okay, I'm glad to introduce you to some of yours. It's you don't need to be introduced, but some others must be introduced. Professor Luke. He's a very good friend of mine. This trip was tremendous for both of us, but finally we succeeded, and he's standing just at this audience, and will present to you the lecture, the microwave to flow paradigm, effective chemical conversions in organic chemistry and catalysis. You are free certainly to listen, and afterwards to ask him any questions. Okay, Rafa, the audience is yours.
Thank you very much. Thank you very much, my friend. Welcome and a very good morning to everybody. It is for me a great pleasure to be here today. Thank you for the kind invitation once again. It has been quite an eventful trip for me to come here this time. Something that, for obvious reasons, we will never forget. We will keep in memory for the rest of our lives and our careers. But eventually, all is well that ends well. And fortunately, I could make it today. And I could be here delivering this presentation. Once again, thank you to my dear friend, Professor Leonid, for bringing me back to Ruden to spend some good time with good colleagues, old-time friends already. It's been a pleasure to have been working and have been part of this wonderful place and university for the past 6 years already. It's been a long time, significant in my career. Okay, so the topic that I bring today in my lecture is actually related to something that is very important for organic synthesis, for catalysis, that started to revolutionize a little bit the topics that we have been seeing in synthetic organic chemistry and in catalysis, I have just mentioned, on the microwave to flow paradigm. So this is a very relevant concept that I want to explain today in detail, exemplified with a number of relevant and interesting concepts and examples that will be able to change also a little bit the synthetic organic chemistry and the catalysis communities as we have seen them in the past few years. This relevant concept is able to facilitate the translation to some of these conditions that we will see that are present and the microwave irradiation into a more scalable and industrially applicable continuous flow process. So this is, in essence, the concept as such. And of course, if this one wants to work at some point, that it's not working. Okay, good. You will see that one of the research topics that we have been working in collaboration with my good friend, Professor Leonid Voskresensky, our dearest dean of the Faculty of Science, is in fact flow chemistry. And it all started as a very nice story. You will see that I like stories. And so far I have been good telling stories. So journals buy the stories, and people buy the stories, industry buys the stories, so I think I'm a good storyteller at this stage. And then these flow chemistry protocols have actually made possible to interact already with industry, as I said, towards these more scalable and applicable concepts. And today I want to exemplify them not only for organic synthesis, that is one of the topics that here most people in the audience are involved with, but in other cases also for materials engineering and design on the basis of catalytic applications, as well as some biomass-related concepts. So towards the end of my presentation, I hope to be able to show you a microwave-to-flow paradigm for lignin conversion, or aromatics conversion. That is the most recent concept that we have developed as part of the ongoing studies here that we are conducting in Ruden. So I hope that, okay, good, thank you. So we start, of course, with the concept of microwave, something that perhaps you are more or less familiar with. For those that are not very familiar, of course, microwaves are an electromagnetic non-ionizing radiation. So microwaves do not have the power per se to break bonds. So whatever people say about microwaving food and potential, harmful effects and so on and so forth, of course, the harmful effects to the food are in terms of dehydration and other types of reactions that take place in food, but not because microwaves themselves have any power to break down bonds, organic chemistry bonds. So this is something very important that I want to bring here, because it's actually a non-ionizing radiation. So it's a very safe and absolutely and completely non-harmful type of irradiation. I hope that this is clear, because the location actually in the spectrum that you see in there, oh, this is nice in Spanish. I have some good stuff in there. So if you move to the next slide, please. Thank you. We bring actually the effect and how do microwaves hit. For those that are not familiar, of course, we do have two types of effects under microwave irradiation. When we have a solvent type of effect, we have this dipolar polarization heating. If you can click, then they can see, the students and the audience can see that the dipolar polarization heating, it's one thing. Don't click. No, go back, please. Go back, because we have to keep the carbons going. Okay. And now it's gone. Go on. Anyway, so we do have the dipolar polarization effect, which is the molecules, what they have dipoles, and then they hit with this spontaneous dipolar polarization that is translated into the solution. When we have solids, because we do have, for example, polar solids, such as carbons, in which the movement is not the dipolar polarization, but the Maxwell-Wagner effect. That means an electron type of polarization that keeps this moving, and we have this translation into heating into the reaction media. So we have these two different types of heating effects in microwaves. For those that are also familiar with microwave irradiation, there have been a lot of controversy about the so-called microwave effects. I have a couple of colleagues that go on one side or on another side, so there was a big fight long time ago. Now people are more calm and more relaxed, but at some point there was a big fight related to these microwave effects. So is there really a microwave effect that provides the special reaction conditions, the special yields, the special selectivities that we normally see in microwave-assisted irradiation reactions? Or this is just a purely fast heating and localized heating in solution that is normally what we see? There has been a lot of controversy on this topic, okay? I'm not going to side with one or the other because some scientists have demonstrated some kind of microwave effects, not very clearly, but what is clear, and then we go to the next slide, so you see the electrons moving again. What is clear is that microwaves, in fact, are able to heat these solutions very differently as compared to the conventional heating that we observe in reactions. So conventional heating is obviously taking place firstly on the vessel itself, and through convective heating, this heat is dissipated, is incorporated into the solution. Okay, so this is clear. This is the way that you heat an oil bath. This is the way that you heat your pasta or your rice when you cook at home. It's essentially the way that you normally cook chemistry, in the same way that you cook food. But when we have microwave irradiation, the effect is actually very different, because normally this dipolar heating that we have in solvents, and you have seen these molecules like moving, the electrons moving also, we have a direct heating of the molecules into the solution. It's completely the opposite. In here, we don't heat the walls of the vessel and then the translation towards this convective heating. We have the direct heating of the molecules that are present in the solution, of these polar molecules, and then, of course, through this localized heating, we have dissipation. But normally it's opposed as compared to conventional heating, because the walls are not normally heated. The reaction media is heated directly into the molecules that are able to transfer this energy from microwaves. So essentially, the temperature gradient in microwave-assisted reactions and conventional heating is remarkably different. And I hope this is well understood, because essentially this is what conveys the great properties of microwave-assisted or microwave-induced reactions. This very localized, spontaneous, fast heating, ultra-fast heating in some cases, depending on the polarity, of course, of the molecules, of the solvents, and so on and so forth. So in here, the potential, again, it's on the remarkably different heating, which, if we move to the next slide, in fact, you are going to see that allows for the design of tunable type of equipment in order to make this microwave heating possible. And in this way, I have brought a few commercial, of course, and non-commercial and homemade multi-mode systems. So these are not focalized. We have two types of microwave reactors, as you may know. We have focalized heating, the so-called monomode, in which we normally use a particular wavelength, a particular frequency, in order to have with a magnetron this source of very focalized microwave irradiation. But normally what you have at home are these type of devices. I mean, not so sophisticated as you see, because this is a modified one, this is a tunable one. But what you have at home is a non-focalized system. You have a multi-mode type of system in which you get an average of microwave radiation with different modes, with different waves, in order to cope with this energy of microwaves. You have the magnetrons in here, that is actually quite nice, and then you have in here an image, a photograph on how the system looks from the inside. There are also some commercial devices, maybe this Ethos, that is perhaps the most well-known device for microwave multi-mode system. And this is why I have included in here. But if we move to the next slide, we have also the monomode systems. And the monomode systems, in this one, you have very focalized microwave energy at a particular wavelength that is able to activate these molecules. The star, of course, of all of this is Anton Parr. So this instrumentation actually has the best performance and a very optimized monomode of microwave radiation in order to selectively activate these molecules. But in any case, most of these reactors, maybe you know CEM, that has been, for many years, was, because we're talking about past. For many years, it was the main company, the main development company on microwave irradiation reactors. But there are others. CEREM has become actually a top competitor in the market. This is a French franchise. And in fact, as far as I remember, probably she's still there, there was a Russian lady, a Russian female, that was in fact managing the business for CEREM for recent years. I have been in touch with her because we started a cooperation. And now they even have something that I will disclose today in the microwave to flow paradigm, a continuous flow microwave reactor, which is the hybrid in which what I will discuss today, in between microwave and continuous flow. So they have a similar instrumentation to this one that is a microwave continuous flow. There are others, of course, in here, the Biotage and other types of companies. But Anton Parr and CEM have been by far leading the market in this instrumentation in terms of monowave, in terms of very focalized microwave irradiation and heating. So in order to illustrate this, of course, with some numbers for everybody to be able to understand, let's talk about a very simple reaction, okay, a model reaction. And then I will work out the translation from microwave to flow. I will bring now, in a while, the microwave to flow paradigm. So microwave irradiation, very fast and homogeneous heating, as we have discussed. We have the ability to promote a number of reactions. For organic chemistry, you're going to see some really cool compounds coming up in a second. And we can combine this to make it more attractive for materials design, for catalysis, for a number of different strategies. So it's not only restricted to synthetic organic chemistry. You're going to see some examples, some mixed examples. But in essence, it allows for a lot of relevant and interesting insights into chemical reactions, into synthetic organic chemistry processes, and other types of possibilities. The example that I bring you here, to start with, as I said, from which I'm going to take to explain the microwave to flow paradigm, is a very simple alkylation of toluene, okay? There is nothing fancy in these chemistries that I'm going to show. It's pretty simple, it's well understood, but it's a relevant reaction because it's extensively used in the petrochemical industry. So alkylation reactions are very important for petrochemicals because many of these derivatives, in fact, are involved in blends, in mixtures to particularly improve the octane number of gasolines. Okay, so for those that are not very familiar with petrochemistry, I keep it very simple. So you have a gasoline that improves its performance, just to keep it very simple, by the addition of these compounds. You have a better gasoline by the addition of these compounds. That's it. Your car, goes well, and it improves its performance. I'll leave it there. On some other day, I will explain this in detail, or if anyone is able to, or is willing to know a little bit more, you can ask at the end of the lecture. So this is a very important chemistry. As I say, it's relatively simple. It's pretty simple. It's well understood. So nothing particularly fancy in there. But it's a reaction that you can conduct and you can actually perform under microwave irradiation. So under very, very short time of reactions, and not very high temperatures, in fact, around 110, 120, this is the maximum temperature that is reached. The average temperature stays at around 100 degrees C, so mild reaction conditions, very short time of reactions, and the microwave irradiation, you can achieve pretty good yields. Again, to make a long story very short, you can achieve pretty good yields to the target products. Target products are alkyl derivatives of toluene. That's it. Let's leave it there, okay? You can use different catalytic systems. I will bring the systems and the details on another occasion, because this is the important thing, is the microwave to flow paradigm for today. And you can perform these chemistries in order also to improve the selectivity to the ortho-alkylated product. That is not the thermodynamically favored, as you know, that is the para, the less sterically hindered product. But still you can push the selectivity to the ortho-alkylated product by conducting the reaction under microwave irradiation. As opposed to conventional heating, we have advantages. Very, very fast reaction times, typically 3 to 5 minutes. I mean, in order to perform this reaction under conventionally heating conditions, you can spend hours, at least 6 to 12 hours. This you do in 5 minutes, 3 minutes. Which is pretty good, right? And in addition to this, you can also influence and vary selectivity, which is another added advantage of this. So then, the good thing is how to translate this into a more scalable process, because at the end of the day, I'm doing this reaction in a very small microwave of this size. Very small. Lab scale. If I want to improve the quality of gasolines for 2 million cars that probably you have here in Moscow, I think probably more than 2 million cars, right? Probably you will have 10 million cars here in Moscow. Well, I think it doesn't work out. No, if I do this in this very small microwave benchtop reactor, I don't think it will lead me anywhere. So how do we translate this into a more scalable type of system in order to be able to, of course, sell this type of additive to be added into gasolines? Well, this is, in essence, the microwave to flow paradigm. Translating optimized conditions from microwave irradiation, in which we are going to see that we have a significant parallelism as compared to flow reactors, into a more scalable system. I have my benchtop microwave reactor that I want to translate into perhaps a little bit larger system, and the continuous flow path in which we can produce continuously milliliters, liters, and tons of these type of additives, fuel additives, gasoline additives, in order to improve the performance of gasolines. So we take this parallelism in order to provide access to the flow reactors. In microwave reactors, of course, this is something that I did not discuss in detail, but perhaps you can already imagine that you have this very flash heating, very rapid heating, that, as I said. You are interacting directly with molecules. You are not heating the vessel, the walls of the vessel, and you don't have this convective heating translating into the reaction medium. So you have a very selective, localized heating on this dipolar polarization effect that I said, if you have a liquid, if you have a solvent, if you have a reagent, and then if you have a solid, if you have a carbon, for example, you have the Maxwell-Warnag effect that I mentioned. Okay? So we have this very nice and rapid heating. At the same time that we have, of course, high pressures. Normally they are below 30 bar, but it could be 10 bar, it could be 15 bar. So you have a relatively high pressure in the system that develops when you have this type of spontaneous heating, and then the molecules are heated under high temperatures, of course, below 300 degrees C, but certainly the 100 that I have selected for this particular alkylation is very low, as I said. These are very mild conditions. In many other cases, you have reaction conditions that are quite extreme, 200, 250, 270. You can achieve very, very high reactions under microwave irradiation. And I did not bring the example today because I wanted to focus on catalysis mostly and organic chemistry. But we have a very nice example similar to this one, in which the maximum, the optimized conditions for this example, that is nickel zero-valent magnetic nanoparticles, just to make a long story very short once again, reaction conditions were close to 300 degrees C. And that was the optimum. Under these type of conditions, almost 30 bar, 280 degrees C, we could synthesize around 70%, 70 to 80% in terms of yield for these nickel zero-valent nanoparticles under these optimum conditions in just, not 1 second, but in just a couple of minutes, 1-2 minutes. Again, ultra fast, but very severe, very intensive reaction conditions, okay? As I mentioned, we have good parallelism between microwave and flow, but in microwaves, of course, we have two big important issues. If I have a small bench type of reactor, I cannot manage to do anything at relatively large scale. So we have a system that is not scalable. And for those actually working with a very nice reactor, hopefully we will see this. Okay. I shouldn't disclose this. This is the work of the dean, so I shut my mouth. There is a possibility in order to work with this type of system safely, but if you have ever worked with a microwave reactor, you can have some issues also there, okay? It's not so safe, particularly working with a small reactor system at a very extreme conditions, temperature and pressure, most importantly. So if you are not careful enough, and then we will see how to manage this next year, you can have an explosion. And this is not what we want, right? We want to be safe, and we want to have a safe environment in the lab and in practicals, in demonstrations, and also in research, okay? The issue from here is that we have this headspace, of course, that in combination with the high temperature and the high pressure makes the whole system very unstable, okay? So to speak, in a very simple way. Then explosions happen, okay? This is a generally well-known drawback of microwave-assisted irradiation reactions, particularly for extreme conditions. So if we are going for very high temperature, very high pressure, these type of systems, okay? 30 bar, 270 degrees C, you are entering what I like to call the explosion regime, okay? Danger. Everything is starting to be flashing red. So you have to be very, very careful. Particularly if you work under these very extreme reaction conditions with aqueous media, with water, with methanol, with combinations of these two, I think you have a very high chances that your reaction will not succeed, but it will end up into a big explosion in the lab, okay? It happened to us recently in my former lab in Spain, and this happens, you know? this is, it's a reality. The explosions take place, are more than possible, and this is due to the issues with the headspace. So the microwave to flow parallelism and parallelism in terms of conditions that we're going to see there, and paradigm is actually not only going to bring us to a more scalable system, but also safer, much safer. Because in there we will see, we can manage to control some of the parameters that we are unable to control on the microwave radiation. So this is the reason why the microwave to flow is one of the paradigms for a more sustainable future, for synthetic organic chemistry, for catalysis, for materials design and development, and so on and so forth. In flow reactors, we have this very fantastic parallelism. This is what we love. We still have the very flash heating, because of course, in these very, very micro and nano channels, of course, there is an enhanced mass transfer, and we can also have this very flash heating. We still have the high pressures in here, a lot larger. So this is another good thing. But the advantage is that, we will see later, we can control these very high pressures with a back pressure regulator. It's a lot more controllable than in the case of microwave reaction, in which we leave the reaction to develop an internal pressure that can lead to the explosions due to the headspace. The relevant advantage as compared to microwave radiation is that in flow reactors we don't have headspace. The nano reactors, the microchannels are so small, are so that we don't have the possibility to create any of this headspace. So essentially, the explosions that were possible and actually rather likely to happen under very extreme reaction conditions are completely minimized, circumvented, and avoided under continuous flow conditions in these nano channels, in these micro channels. We have different possibilities that we're going to see in a while. So this is really nice. We have high space-time yields because of this enhanced mass transfer, and regardless of the high temperatures, as you can imagine, they are high. This methodology, yes, it's scalable. So in here, we have the additional advantage. No explosions and a scalable system. And in this type of systems, we will see, we will be able to continuously produce our target product. Of course, firstly, we need to optimize the reaction conditions in order to make it possible, but in essence, we will be able to generate our target product and to continuously produce it, going from milligrams or milliliters, okay, we start with micro, going from micrograms or microliters to milliliters to liters at the minimum, and if the instrumentation, the continuous flow instrumentation is large enough, we could go even to ton scale. I'm going to show some examples in a little while. So this is essentially a summary of what you do on the microwave, and we will translate under continuous flow. We have only, come on, nothing is perfect in this world, okay? There is no perfection. So we have one important difficulty, one important challenge that we need to solve, as you can imagine, in continuous flow chemistry, that is working with heterogeneous reaction mixture. So in order to work well under these nano channels and micro reactors that we're going to see in a while, we need crystal clear solutions, and working with solids in suspension, oversaturated solutions, it's a significant challenge. So, I mean, the instrumentation that is available now, even at commercial level, can partially cope with some of these issues. But in the past, I mean, this was the main challenge for continuous flow chemistry. It still remains the main challenge for these continuous flow processes. When you have something that crystallizes into solution, an oversaturated solution, an intermediate that is poorly soluble in your solvent, in your mixture, and then you start to have a solids in suspension, this is a mess. It's a complete mess because essentially the channels are very, very thin, as you can imagine, nano channels, micro channels, and then they get clogged very easily. So then the whole system stops. And this can be a nightmare, okay? Because we have been extensively working with these systems, and when they clog, it's again, you need to stop, you need to understand what is going on, you need to do a lot of cleaning, and restart from the beginning and try to optimize conditions in order to avoid the presence of these solids in suspension or these inhomogeneous reaction mixtures. So, I mean, it has a lot of advantages, of course. It can provide a significant benefit as compared to microwave reactors, but of course, its own challenges that came precisely with this type of concept. And okay, we move to the next slide because I could bring this back again. You have seen, you remember microwave, now we translate it into flow. And then I will tell another story. So this is the same reaction, you see, nothing fancy in there. 3 minutes under microwave irradiation, you have, yields of 60, 70%, depending on the reaction systems. When you bring this under continuous flow, you can improve the conversion and even improve more the selectivity to the orthoalkylated product. But you are making the translation. So in essence, you have a very similar system. High temperature, high pressure, but now you have no head space, hence no possibility of explosions, and you have a scalable system. In 3 to 4 minutes, now you can go from 60% that you were, if you go back one slide, please, you will see 95%, no, before, yes. So you see, maximum was around 60%, but the average is around 40%. So from 40%, and now we move to the next slide, you can move to 95, 97, 98%, improving also the selectivity to the orthoalkylated product. Same more or less reaction time in this case, in continuous flow processes, it is called the time that the feed interacts with the catalyst. It's a different type of concept. It's residence time. Okay, it's not reaction time, but it's residence time. The residence time that your reagent is actually in contact with the catalyst or in contact in the system. So it's normally called residence time. But this is really interesting because you can push the conversion. You can, in some cases, also improve the selectivity. But the most important thing is that in the microwave reaction, you are able probably to generate 40, 60%, talking about milligrams of products or milliliters of products. And in here, you can go to hundreds of milliliters if you want, or even to liter scale, because you can do this reaction on the continuous flow mode and to generate milliliters, 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 essentially pushing the boundaries towards these continuous flow conditions and being able to generate larger quantities of product. These are relevant products, but if we move on to even more complex systems, and for this we can go to the next slide, this also works very nicely for very complex organic compounds. Spiroindoles is one of the examples that I bring here, okay? But in here you see how cool is this, because we have complex chemistries happening. We have complex cyclizations, we have complex CH activation reaction. In essence, this allows for a number of complex chemistries, synthetic organic steps, to be translated from microwave to flow. And here comes another nice story, okay? So the story is the design of catalysts for this reaction, for this cyclization to take place, okay? This works for racemic type of compounds, but even for enantiomerically pure compounds. Depending on the selection, of course, the reaction will be able to work for enantiomerically pure compounds. I don't have it in the slides, again, for the sake of time, but probably towards the end, I will provide another example on another set of organic chemistry reactions for the synthesis of menthol. And it's a similar type of concept. It was firstly developed under microwave conditions, and then it could be translated under continuous flow, both for racemic type of compounds, but also, and most importantly, most interestingly, for enantiomerically pure compounds. So the story goes like this. We designed some catalytic systems based on gold. So these are gold-supported nanoparticles on a mesoporous material, okay? No need to go into detail. If you want to know a little bit more, this was the cover for green chemistry and also advanced synthesis and catalysis for many years, even in green chemistry. And these are the examples, okay, that illustrates that the reaction works nicely under microwave irradiation. So using this gold system, we were able to promote this cyclization in order to provide access to these spiroindoles. Works with conversion and works with isolated yields. So as you see, 94, 96, 97 isolated yield for different entries with different solvents, with temperatures, even temperatures as low as 70 degrees C. So the presence of the catalyst is able to promote these chemistries even at temperatures as low as 70 degrees C, and the microwave irradiation. Okay? Microwave irradiation. What was the issue here? Which is how the story unfolds now. The issue here was that for other more complicated substrates, which is the additional advantage in flow that I did not mention until now, but you're going to see it now with the example, is that for other challenging substrates, we were unable to get this reaction promoted. So as you see in there, we tried the best we could, and we could not succeed, okay? Under batch conditions, conventional heating, conventional microwave irradiation, it was not possible to promote this type of, well, anyway, a lot more challenging cyclization to generate this complicated spiroindole product, okay? So we tried a number of different chemistries, same type of system, a larger load impossible, 10 mol%, temperatures between 80 to 100 to 150, 48 hours, 1 hour microwave irradiation, nothing. Nothing was really working on this, okay? But the interesting thing is that when this work was translated into a continuous flow protocol, we could indeed, with a little modified reaction media, okay, I understand that it was not a complete translation, that we needed to optimize some conditions, but from negligible yields to 80%, I think it's a big difference, right? It makes a huge difference. Reaction that was not working, as I said, 1 hour microwave irradiation, 48 hours conventional heating, we were able to promote this reaction under continuous flow conditions, under this microflow type of reactor, same catalyst. The reaction mixture was a combination of ethanol and water, okay, and the reaction had to be pushed a little bit more. But the residence time is another thing that I want to draw your attention to, because the residence time could be reduced to a minimum of 5.5 minutes, almost 6 minutes, which is very remarkable. You see in there. Reactor volume, the flow, all the optimized conditions are here. We could even push this to complete conversion, quantitative conversion. So what is really going on there? I mean, there is no magic. There is no secret to success in this type of chemistries. The secret to success, I will come back to this one. You can continue. You are going back. Forward, please. So there is no secret. I just want to bring the advantages. Please keep. Over. No, but not back. Oh no. Oh. Yes. Okay. Keep moving. I will come back at some point. So yes, the next one, the next one, the next one. This one, okay. There was no secret to this success. It's just one of the main advantages of continuous flow processes. That, of course, you have some challenges that I mentioned, but you have these significant advantages. And one of the most significant advantages that I want to bring over to this microwave to flow paradigm is illustrated here, different from the scale-up. The improved environmental impact, but of course, safety and the processing times. There is a significant enhancement of mass transfer. I don't know if, are there any engineers, chemical engineers in the audience? I think this is hardcore organic synthesis, organic chemistry. No chemical engineers, okay. So if it was a chemical engineer, I would explain into a lot more detail, of course, and this person would really appreciate because it will be his or her background, on this enhanced mass transfer that is achieved under this type of continuous flow conditions. We are going to see in detail in a while, so now we come back. We come back to the slide. Yeah, another one more. Yes, this one. So a lot of relevant chemistries, in fact, can be performed under these continuous flow conditions. And this is, the story is not unique to these very complex spiroindoles that are beautiful organic compounds, but also to, as you see, coupling chemistries, other CH activation chemistries, selective oxidations, in this particular case aerobic oxidations, name it. I mean, there are a lot of relevant chemistries that you can translate into or from microwave-assisted irradiation or conventional heating into continuous flow. And these are a couple of additional examples. Also from the group, you see from a long, long time ago, almost 10 years ago in some cases. Time really flies. We have been working with this topic already for almost 15 years. So A3 couplings, you see with these beautiful colors. So you have some colorful compounds in there that you can produce. And you see actually how the color starts to develop with the production of the compounds, and you do a column chromatography, and you have these very beautiful colorful products from these derivatives of these A3 couplings. You see in there not so very high reaction conditions, so not always you need extreme reaction conditions that again counteract against the safety that I have just mentioned, so this is good for safety purposes. Normally very moderate to very high pressures. This is clear, but again, you can push, you can maximize yields. We are talking about, in this particular example, of residence times in the order of minutes. Once again, minutes. So we don't have to go for many minutes or for many hours as compared to conventional heating for sure, or even other microwave irradiation. And in other cases, we can also design other relevant systems in order to make them work for selective chemistries, for selective aerobic oxidations. This one is relatively simple, but it works nicely. Moderate temperatures, relatively high pressures, and in some cases, you need a little bit longer times in order to make this happen. But in principle, it works very nicely for some of these examples that you are starting to see in this particular regard. So before moving in there, how am I doing with time? Okay, I think I'm doing well. But I cannot take too much time in the coming slides. So this is an example that also illustrates a similar system with additional advantages for biocatalysis. So I'm not only and exclusively disclosing examples in synthetic organic chemistry, in catalysis, but also, it's gone? Okay. In biocatalysis. So the example that I was showing in here, The example that I was showing here is a biocatalyzed process in which we design an encapsulated lipase. A lipase is a biocatalyst, it's an enzyme that we encapsulate in a porous silicate material. And this encapsulation allowed, in fact, for the utilization of a waste feedstock. So the waste feedstock that we utilized is a refined palm oil feedstock from waste in Brazil. So the photo that you saw, and I hope that you will see soon back again in the slides, is with a very good friend, another very good friend of mine, Professor Rodrigo de Souza in Rio de Janeiro. I like Brazil, definitely much better temperatures that you have here in Russia, I'm afraid. And much nicer beaches and, and other places. Also, you see, good. So this guy, I'm here in front of the Pau d'Azucar. This was a long time ago. But as you see, these biosilicified lipases are able to work towards this generation of emulsifiers, Solketal, relevant organic compounds for different applications based on this continuous flow system. So it's not only applicable for organic synthesis, for catalysis, but even for biocatalysis under certain conditions. The take-home message of this slide is also the stability of the system under these continuous flow conditions. This was specially achieved for this material. I won't get into detail, but you see, residence time relatively short. So we're talking about a few minutes. It can go up to 48, 50 minutes for more challenging compounds. But in essence, for those that are not so challenging, we can achieve very high yields, conversions, 80, 95%, and relatively low residence times in the order of minutes, okay? Good, so now we can move on to the next slide. Again, pros and cons that I think should be clear at this moment already. Inherent safety, better yields. In some cases, we can also influence selectivities. In general, low capital investment. Okay, because many of these systems can be fine-tuned. I'm going to show you, and then we will have the opportunity to develop something in the labs here. And a very nice setup that the students will be able to work with safely, even with some hazardous reactions, swiftly, with shorter processing times, and being able to develop potentially novel chemistries, such as those that I have mentioned for the challenging spiroindole compound. In some cases, you can even develop some novel chemistries. The scale-up, as you have seen, is relatively straightforward. In there, we have the possibility to scale up to produce multi-grams, multi-milliliters, and even liters. So less inventory is needed. You just need the very nice setup that you can prepare in a homemade way that you will see in a little while that will lead to cost savings and improve product quality. Because at the end of the day, you are also compensating in a continuous process for the multiple step separations, purifications, if you are doing a multi-step synthesis. So essentially, everything comes up with a better product quality, avoids all these intermediate steps, and with an enhanced and improved environmental impact. As I said earlier on, this is also very clear. It's a beautiful tool to work for synthetic organic chemistry, for catalysis, for materials design and development, but of course it's far from being perfect. There is nothing of such kind as this perfection in life, okay? So we have a number of challenges, okay? The first three actually are more related to industry. You know, industry are still in some processes, in some protocols, some methodologies are still reluctant to make the change, make the shift towards continuous flow processes, because essentially their batch processes are well understood. They have been using them for 50 or 70 plus years, and they feel no need to change their process as such in order to become, you know, a more scalable, a more sustainable, a safer type of process. But in essence, we still lack of adequately trained people and the adequate mindset in order to make the transition happen. And this is what I'm trying to do today and what I will try to do in the future, to start from this transition, of course, at university level, but so that this trained individuals can lead this translation into the future. And this is the important thing. We need more trained people, and we need these new engineering and operating skills. Everything else that you see, I have already discussed. The limitations with solids is the most disadvantageous as compared to any other conventional heating, microwave, and so on and so forth processes. But essentially, the others are all, a matter of the needed mindset change. And this needs to start, of course, at university level. It needs to start with scientists in order to push for this much needed change. So if we move to the next slide, now we are going to focus a little bit more on flow. And the good thing about this is that some of the advantages that have been mentioned are very, very significant. And as I said, one of the most relevant ones that was the one that provided access to this very complex and very challenging spiral indoors in this cyclization step is, in fact, this micro-mixing that is achieved under these continuous flow conditions. The enhanced mass transfer and the micro-mixing are actually very favorable in order to push for these novel chemistries, multi-step processes, and avoid some of these tedious and complicated separations, purifications in multi-step processes. So this is actually very, very advantageous and combines with the efficient heat transfer and the temperature control due to the high surface to volume ratio. These are the two key advantages of continuous flow processes as compared to batch chemistries, including microwave-assisted reactions. The enhanced mass transfer takes place in O and allows for multiphasic reactions to be also favored. And there are, of course, many other advantages, but these three, as I said, are critical. Of course, we have another interesting thing that is the automated purification. So we can combine this continuous flow process with membrane technologies and other types of purification methodologies, and it allows for this integrated analytics and characterization as well as screening. So we have many of these lab on a chip. I don't know if you've heard about this concept that is actually very nice. The lab on a chip allows us to conduct this flow processing, many of these for the synthesis of materials, also not so much for organic synthesis, but for material synthesis and similar fields. So if we keep going on this, of course, for the sake of time, and I think I don't have actually much time left. Probably I should have, around 50 minutes or so. Jeez, I spent already too much time, but this high efficient mixing and this micro mixing actually takes place under continuous flow conditions, and of course these examples are actually the proof that demonstrate this. A batch as compared to a team mixer, but as compared, for example, to the micro mixing. You see the micro mixing significantly enhances the yield to product by this very, very efficient micro mixing in the micro or in the nanoscale. So these are the very fast organic synthesis that can take place in microreactors. Professor Yoshida, unfortunately, he passed away a couple of years ago, but he was one of the pioneers in continuous flow processes for this type of impossible chemistries in batch that he developed already a long time ago, but also to demonstrate the advantage, the significant advantages that we can achieve in continuous flow processes as compared to conventional setups. So these are relevant advantages that are illustrated in there. And also something that I have mentioned before, the high surface to volume ratio. And we have now even some nice music in here. By controlling also exothermic reactions, we are able to control exothermic reactions. In microwave-assisted protocols, it's very challenging, so you have to be very careful of the explosions. But in here, you can control exothermic reactions, again, by performing these very flash chemistries and having also a possibility to have these microreactors with heat exchange capabilities. And these microreactors with heat exchange capabilities actually can take us to, again, the next set of chemistries, impossible chemistries that we can perform in batch. Very exothermic reactions, very endothermic reactions under extreme conditions. You have seen in the previous slide, the one before, yes, reactions, impossible chemistry. How you are going to perform a reaction at minus 70 degrees C, minus 100 degrees C. This is, a significant challenge, but it can be actually performed with yields close to 70%, So in here you have, these impossible chemistries. I go for the very low temperatures, but again for the very high temperatures. The very high temperatures, we need to have a heat exchange capability in the microreactor in order to avoid the explosion, and avoid the overreaction and the generation of 300 degrees C, and then boom. Okay? So we are able to work under extreme conditions with these microreactors using heat exchange capabilities. And this is a very relevant feature of the system that you can create in any lab in the world. So this gentleman here is going to do some good work for you all, because this is actually a very, very simple setup that you can design using a couple of pumps, a couple of peristaltic pumps, easy, a mixing unit, a reaction zone in which you can do a lot of different chemistries. You can cool, as you have seen. Hopefully, you will not need for your reactions minus 70 degrees C, then it will be not so easy. But normally, you will heat. And heating could be, again, at a reasonable temperature. 70, 100, 150. So depending on this, you have different possibilities. Also in here, you have empty coils. You have the lab on a chip, or the chip type of design for nanomaterial synthesis of cartridges in which you just set up your catalyst or your system, and you can do all the continuous flow reactions with it. There is an additional possibility of the combination of visible lights, LEDs, or an UV lamp. And in this case, you have photoredox flow chemistries. And this is even more exciting because you can do these photoredox chemistries under continuous flow conditions. So this is something, but it's a very simple reaction setup. Heat exchanger only if needed, quencher only if needed, and this is the most important part, the back pressure regulator in order to keep the whole system under pressure, in order to mimic the conditions that we have under microwave irradiation. So this is the microwave to flow paradigm. But as you see, this is a very, very simple setup. Very, very simple. Of course, there are many commercial systems that are already taking care of this, and we will bring something exciting to the lab soon. So we have Thales Nano with the cubes, we have the Asias from Series, there are the Chemtrix. Vaportech is actually one of the leaders for the photo flow. These have photoredox continuous flow that are equipped with different LEDs and UV lamps so that you can perform photochemistry under continuous flow conditions. These reactors are very cool, very, very cool. And future chemistries, anyway, lots of them under different sources. And there is a very nice Chinese brand that is able to combine also continuous flow with photochemistry. So we will see more developments to come soon in this particular regard. And we do have, of course, the homemade systems. So you can actually develop and you can actually install a very simple setup that is able to work under these continuous flow conditions. Okay, these are some examples that I wanted to bring because continuous processing, actually, in fact, this was much later. It wasn't like in 2019 or 2020. A couple of years ago, continuous flow processes came up top of the list in terms of priorities, for example, for pharma processing, for pharma synthesis. So these are chemistries that are very much welcome for this pharma synthesis, for this chemistry research in pharma. As I said, this came from a relatively old study, but the latest study, again, continuous flow processes taking top priority in pharma synthesis. And if we continue moving on, in fact, there are already some examples that I wanted to show you on the industrial scale-up of microreactors to produce pharmaceuticals. And this one is a battery of microreactors for the production of these two types of compounds. This is the naproxenodis COX inhibiting nitrogen oxide donator, essentially for arthritis. It's an extensively prescribed drug to patients that have this, these bone-related issues of arthritis. And this is already at a production scale of more than 100 tons a year with this battery of microreactors. I mean, this is not an invention that I'm coming up with these days. This is already an industrial reality. And of course, something that it will be taking off in the future, because this battery of reactors, 96 reactors from Corning, on 2 different towers, are able to generate more than 100 tons of this pharmaceutical. Imagine, this is a pharmaceutical. It's not a commodity chemical, or it's not a simple type of compound. No, we're talking about big business in here. And the big business continues because, of course, our idea is to apply this to make our chemistries more successful, but at the same time, importantly, something that I did not emphasize perhaps so much, but to make our chemistries safer, but at the same time more sustainable. So we are also heading towards sustainability to avoid this type of multiple separations, overreactions that I have briefly mentioned, energy over-consuming, protecting group-free synthesis for all of this, and at the same time, improving the conversion, improving the selectivity, improving the green credentials of our methodologies, of our reactions. So essentially aiming for greener and more sustainable chemical synthesis, something that we can achieve doing all of these microreactor technologies and the flow approaches that have a lot of relevant and inherent advantages with respect to sustainability. Until now, I did not talk about sustainability. I talk about big business, safety, but also we have a lot of interesting advantages in terms of sustainability. Of course, the scalability you have already seen, and the safety. But at the same time, of course, we are improving the green credentials of the reactions by saving times of reactions, minimizing the screening, minimizing waste. Of course, if we don't have to incorporate subsequent separation, purification strategies in the chemical synthesis, of course, we are minimizing the production of waste. And at the end of the day, these are processes that are more energy efficient and more cost effective. So everything adds up to a concept that is actually going to bring us a more sustainable future. And the more sustainable future, I wanted to illustrate in a couple of examples. Not, you have already seen some examples, but some very cool examples. So the first example that I bring you, that some of you already know from my previous visits here, is the waste to pharma concept. And the waste to pharma concept, in fact, for us started already quite a few years ago through Evan, that was a student of my good friend, Professor Frank Gupton. He's based in the US at Virginia Commonwealth University. But Frank spent more than 40 years in industry, in the pharma industry. So he was a big chief of one of the largest pharma companies in the US, and started with the movement of continuous flow processes for pharma design, synthesis, and discovery. So the story goes like we have been friends for a long, long time, and then he started a new program, heavily funded and subsidized by the Bill and Melinda Gates Foundation, named Medicines for All. In essence, to prepare and to design cheaper medicines for the third world countries, for many places in Africa and in India, South America, and places all over the world. So we had the pleasure to host Evan in my lab at that time in Cordoba, a long time ago, more than 7-8 years ago. And he started, you see, long time ago already, he started to work on this medicines for all concept applied to one of the most relevant molecules that we were working with that is going to appear here, humans. So this is actually a side product of biomass processing. And the side product of biomass processing that you see the structure in there stems from the subsequent dehydration, hydrolysis, and decomposition, as well as polymerization of sugars, hexoses and pentoses, derived furanics, HMF, furfural, MMF. So this is an actual example, proposed example of what the human's molecule looks like. And from here, we were able to deconstruct the complex structures of humans into simple furanics, simple furfural, simple HMF, simple MMF, simple furanic derivatives in order to provide these ways to API, active pharmaceutical ingredients synthesis. We selected a couple of APIs to start with. The story is unfolding, and we are continuing to develop in this regard. But again, to make a long story very short, on the different strategies that we have used and the important considerations that we managed to make, I will come up with a couple of examples that we have recently come up with. The synthesis of ancarolol, an antihypertensive drug extensively prescribed to patients that have coronary diseases. Through multi-step synthesis, continuous flow. In some cases, as you see here, continuous photoflow. This amidation in here is performed under photoredox continuous flow conditions. Then, some simple synthetic organic steps, and we can, in fact, move on to other types of molecules that we can also synthesize. Furosemide is one of the most recent ones by, again, simple conversion of furanics and coupling with other types of reactions that we have performed under continuous flows. It's a multi-step continuous flow approach that has been already optimized in order to yield complex molecules, furosemide, and the next one is prazosin. Similar sort of chemistries, again, combining relevant continuous flow processes with some relatively known organic synthetic steps that we can also combine in the flow platform. So these are some of the examples, even some of them are very recently achieved, so still unpublished, that illustrate the concept of what we want to do, what we will be doing here very, very soon, together with my good friends and colleagues, that we will be continuing, and of course with some collaborations with my former university in Spain and another associated friendly state, of course, of Russia, that is Kazakhstan. So we are collaborating now, Ruden is collaborating now with Nazarbayev University, and my good friend, Professor Nurcan Nuraye, is the PI of this very nice project, Green DG Pharma, that we will be focusing on the design of these novel APIs through continuous flow processes. So we want to do this all from waste, and these are some of the recent publications and some of the projects in which we will be involved in the near future. And then I hope that in the next presentation that I will deliver here, probably before the end of summer, maybe in June or in July, when I will be back for a few days again, I will be able to show already some of the ongoing examples of these continuous flow photoredox processes for the synthesis of some of these pharmaceuticals. Last but not least, I will keep this story very, very short. I wanted to include a couple of slides on this microwave to flow, but I think it's already too late because I have taken too much time. So this is just another example on the microwave to flow paradigm and how we can change and influence selectivity in this particular case, biomass-related conversion. So we have all these relevant molecules that can be derived from lignin. Okay, I will make a long story very, very short because I think I am running out of time already. For these aromatic compounds and for aliphatic compounds that we want to provide access to. And again, to make a long story very short, we were focusing on different lignin fragments in order to provide access to useful aromatics and aromatic-derived molecules. Again, making a long story very short, this is the microwave to flow paradigm. We perform the reaction first under microwave-assisted irradiation. And then when switching to continuous flow, we realized that we can significantly influence the type of chemistry that we can perform. And we can move from transfer hydrogenolysis to hydrogenation. So it's a very interesting paradigm that, again, if you are interested, you can soon check the papers. I will discuss about them next time. But I want you to see the colors, just the colors. It doesn't really matter the product or anything, because, again, as I said, it's a long story. These are the two most recent publications from the group. And then you see the colors in there, how we can influence the selectivity by changing the time of reaction, the catalyst loading, you see, black in here, but black gets reduced. The more catalyst you add, the more contribution to another type of product that you can get. So how you can influence selectivity in the systems. And then not only the selectivity, but you see even pushing the conversion towards some products. You see how the colors are actually changing by just switching from microwave to flow, but even within microwave and within flow, reaction conditions. Okay, so this was something that we could certainly influence to a lot of stage. Reactions and catalysts that are also very stable under continuous flow conditions as well as under microwave irradiation. Okay, so again, a long story made it very short. I made a proposal here on the mechanism, but anyway, I think I'm running out of time. So let us wrap up and finalize the benefits of microwave versus thermal. This was the continuous flow system, but then continuous flow photochemistry that I just mentioned and that I will talk about on another day, and other tandem processes. Okay, conclusions. Let me allow me at least a couple of minutes just to wrap up and to provide access to these very important translation opportunities. So for those that have worked on microwave irradiation, these protocols have been very successful and have provided an additional advantage as compared to conventional batch processes. But of course, as we have seen, this came up with a number of challenges, with explosions, with safety, with non-scalability, that we can in fact overcome, providing access to continuous flow processes in which we have inherent advantages of safety, of better processability, of high yields to products, on cheaper and more sustainable access to compounds, including organic compounds that we have seen, pharmaceuticals, nanomaterials, that will be the topic of my next lecture on Monday, and so on and so forth. Essentially, in many cases, continuous flow processes will allow us to redesign and to rethink conventional chemistries, impossible chemistries that could not be performed in batch, to make them more sustainable under continuous flow conditions. And in addition to this, of course, the possibilities that we have, as I mentioned, on the very efficient micromixing, on the enhanced mass transfer, on the additional improvements that we have seen, will allow us to perform more sustainable chemistries, again, related to API synthesis, nanomaterials, and other types of products for a more sustainable future. With this, of course, I have a big flag in here and a big thanks to all of you for being here today. Thanks for the support of Ruden. For the past few years, my former group in Spain is still there. I have to be thankful also to them. And other flags that contributed to these developments in the past. Of course, my present is and my commitment is here with my friends, with my colleagues. I hope to continue enjoying this collaboration for many years and this cooperation and continue developing some very nice chemistries into flow. Before finishing, this is my story. Make it your story now, okay? And a couple of additional slides that I have. I'm the editor-in-chief of molecular catalysis, so not only organic synthesis, but catalysis. So, of course, we welcome nice contributions here for Ruden on the journal based on catalysis. And the last but not least, if you are interested in edit a book, that is a possibility that you should think. I am also serious editor of the chemistry in the environment, so feel free to drop me some lines. If you move back one slide, one less, you have my email here, so feel free to drop me some lines, and then, you know, we can take this forward to the next stage. I have taken already enough of your time. Thank you once again for being here and not sleeping and not being distracted. I have seen, you know, eyes wide open for the whole 1 hour and a half lecture that I have taken. Once again, thank you for your time. And now it's time for discussion. Thank you, Alexi. Long. Sorry, apologies.
Thank you, Rafa, very much. For the lecture, the dean has left for some urgent matters,
Yes.
so I will be finalizing this for him. Thank you for coming. That's
My pleasure.
that's a big deed now.
Always
so,
here.
You know, when you have been talking about explosions a lot,
Yes.
and everybody who performed microwave experiments, who performed a lot of microwave experiments, sooner or later got exploded. Everybody.
I think if you have at some point experienced yourself or ventured yourself in microwave chemistries, at least once you have experienced an explosion.
Sooner or later, it happens. And the thing which really a person who does that is afraid of, in my opinion, I did it. I exploded several times, of course. So it's not that you are thinking much about safety, what will happen, but the thing that you need to clean up the microwave reactor very tediously. That's
In addition to this, unfortunately, if the explosion is too big, probably you can break down the cap,
And you will
damage the magnetron, and I mean, it can be
and
even
it
worse
will,
than this.
yes, and it will stop for a long time.
Yes,
and we
this
have
is
this
true.
problem now
Unfortunately,
still.
yes.
So please, your questions.
Thank you for your lesson. I want to ask two very unprofessional but technical
No problem.
questions. At first, when we're speaking about difficulties of use of heterogeneous catalysis, is it substantially impossible to use something like we do when we, for example, dehydrogenating alkanes in gaseous phase, when we pressing our reaction mixture through some cartridge with catalyst? And another question, what about what I think about potential of cyclic flow reactors when we, for example, not to allow solution become saturated, we crystallize in some quantities and drawing it back automatically.
Thank you for your two questions. The second one is a very good question. In fact, I did not. Okay, let's see. Go back, and then I will tell you where to stop. Sorry. I had one of the examples, in fact, for the recycling of the continuous flow. I hope that we can get back at some point. Keep going. And then I will tell you, is the aerobic oxidation. This was actually done with recycling because it was not possible to conduct the reaction under conventional one-pass continuous flow. So this is the possibility that it's open. I think it's the next one, probably. Keep going. Yeah, this one here, okay? So this is not conducted in a single pass. This was with a multi-pass with the recycling, because in this way, we could achieve very good conversion and very good selectivity. Sometimes, the issue is the crystallization or of a saturated solution where you have a problem and you need to go on a less oversaturated solution, and then you need a multiple pass. In some other cases, it's just the nature of the reaction that does not allow for a single pass full conversion on a single pass high selectivity, and you need to recycle over and over again in order to achieve this very high conversion and this very high selectivity. So this is possible, and this is a good solution. For the first question, in continuous flow, you can actually push for this type of reaction. So you can have the cartridge, you can flow, you can do the reactions in the gas phase, in the liquid phase. For the examples that I have provided today, mostly they were in the liquid phase. But there are examples in the gas phase where you can perform exactly what you mentioned in your question. And last but not least, I did not go into additional details in order to make the story more complicated, but we have also the combination of continuous flow with other tools. So we can have continuous flow ultrasounds for continuous flow ultrasonic promoted chemistries. We can combine continuous flow with mechanochemistry to have continuous flow mechanochemistry. Okay, I did not want to complicate the equation so much, just to keep the concept simple and to provide some examples. And we can combine, this I mentioned, continuous flow and microwaves. And there are even some instrumental setups that combine continuous flow with microwaves. More questions?
I think if we have no more questions for now, we will meet again on Monday.
On Monday, yes,
on
Monday we'll be back. I am
please
here.
do
Anyway.
not forget,
will not be back.
on Monday we are coming back again.
Yes, we will be back to talk about a different topic. Monday will be nanomaterials and catalysis. So it will be
different.
It will be still a little bit of continuous flow, but more of other types of conditions. Beautiful nanomaterials, some catalysis, some organic chemistry, a little bit combined. Yes, without disclosing anything else, to keep the surprise for Monday.
Then let's thank our speaker once again.
Thank
you very much.
Thank you for being here. Thank you. My pleasure. Thank you. Okay.
That's all for today, I suppose.
Super.
So thank you for coming.